Hey, physical science. It's Thursday, April 23rd, last day of the week. How about that? I'm on page 498. If you could find that, section 3, the periodic table. I tried many ways to illuminate this thing, and I just don't have the technology for it. So you're just going to have to look back and forth to page 500 and 501. In fact, why don't you go ahead and do that now? Go to page 500. I'm going to tell you a story. It's in the late 1800s, and it was Dmitry Mendeleev. Some people pronounce it Mendeleev. And he was going to organize the 65 elements that we had. Now, today what we have are 92 naturally occurring elements. Do you see where uranium is right down here? Well, everything prior to that, including uranium, can be dug out of the hillside. Now, there are two elements that are in such short supply. That would be technetium right there, number 43, and promethium down here, number 61, that some people say that they are not naturally occurring. But I'm going to say they are, and I'm going to go up to 92. Everything above 92, 93 and up are man-made, natural, synthetic. If you take a look at this little donut-shaped symbol, you'll see the donuts on all of those. And so they include those, and then these right here, and I think we're up to 118 now. And so how do they do synthetic elements? Well, they take naturally occurring elements and they bombard them with protons. And they build them up to these fatter, bigger elements that might only last for a few microseconds even. And they call that research. But you never know, it might come to something good. Like, for example, americium right here, number 95, is used in our smoke detectors. It's radioactive. All these are radioactive. From, let's say, about number 86 on up, from radon up, is all radioactive. In fact, I think it's 84 up. Is the nuclei are so big that they just kind of like jello. They're just kind of like jello falling out of the sky. They're just kind of flopping around each other, and they just kind of disintegrate little by little. Too many neutrons. Anyway, they're just too big and fat, and they just fall apart. Okay, so what did he do? Well, good old Mendeleev's periodic table was built out of 3x5 cards, you might say. Playing cards or something, some kind of cards. And what he did was he took his card and he wrote the name of the element, which is probably the most important piece of information on each block of the periodic table. You can see the name of the element, and then after that is the atomic number. And now our modern periodic table is arranged by atomic number. But the one that Mendeleev made was arranged by the average atomic mass. And he had it a little goofed up because it doesn't arrange by mass. It arranges by characteristics, physical and chemical properties. For example, group 1, which we call family number 1, say alkali metals, okay, alkali metals, they are all very similar in terms of the way they respond to other elements. And that's what he did. He just put the characteristics, physical and chemical properties on a card, and then he lined them up based upon how they react with other elements. And then elements too, they reacted differently. This is called not the alkali metals, but the alkaline earth metals. So you got the alkali metals, the alkaline earth metals, and then groups 3 through 12 are called the transition metals, I guess because they're transitioning toward the non-metals. And then the green elements here are the metalloids. That means they can't make up their mind if they are a metal or a non-metal based upon the temperature and pressure that happens to be against them. They will act differently. And then these are the non-metals, the yellow ones over here. And the groups, they have really interesting names. Like group 13 is called the boron group. Group 14 is the carbon group. Group 15 would be the nitrogen group, and 16 is the oxygen group. Isn't that neat? And then 17, these are called the salt formers, halogens. Say halogen, okay? The salt formers, if you take one of these and hook them up with a metal from over here, you'll have a salt like lithium fluoride or lithium chloride or calcium chloride or table salt, sodium chloride. These are the salt formers, and they're called the halogens. The group on the end, group 18, those are the noble gases. Noble gases do not react with other elements. They are kind of like the knights in shining armor, the nobility, the ones that are up on the mountain. They're exclusive of all the little serfs that are down there working for them. They are nobility. They are noble gases. They do not burn because they don't combine with oxygen. And so they are exclusive, you might say. Okay, and they were the last ones to be found in nature, that kind of thing. They just packed them onto the end of the table. Now, what's interesting is I have a little video clip. I have two video clips today. This presentation, and then also a video clip about how the alkali metals respond to water. And also they show you how you can cut these with a knife. They're so soft. You don't think of metals being soft, but they are. Anyway, you can cut them and you can see on the inside that they're real shiny like you would expect, luster. And metals are also capable of transmitting electricity and transmitting heat. They're good conductors. And you can smash on metals and they flatten. It's called malleability. And you can pull them through wires. You can extrude them through a hole and make them into a wire. That's called ductility. And we learned about those earlier. And those are characteristics of metals. Does the word metal mean solid? No. Metal means what I just told you. There's characteristics of conductivity and shininess called luster and malleability and all that. That determines a metal. Well, then why do you have the solid sugar cube looking symbol next to all of these metals? Well, you have it next to some non-metals too. And you have it next to some metalloids. And the reason that the solid symbol is next to them is because at room temperature, they happen to be solids. Now, any element can be liquefied, and any element can be turned into a vapor if you heat it up enough. So these states of matter up here are simply at room temperature, and you will see there is only one non-metal that's a liquid at room temperature, and that's bromine. And it's kind of a reddish, brownish liquid. And then there is only one solid that's a liquid at room temperature, that's mercury. And you know what mercury looks like. It kind of beads up in little round balls. All right, so good old Mendeleev arranged his table by order of the average atomic mass. But the problem is he messed up. You see, because if you take a look at nickel right here, you see nickel, number 28? Well, Mendeleev would have had him over here in group 9 and cobalt in group 10. Because if you start with iron, Fe, the average atomic mass is 55.8. And then nickel would come next, 58.6. And then cobalt would come next at 58.9. But those two are not where they belong on the periodic table for Mendeleev. And in fact, nickel should be over there in group 10, and cobalt should be over here in group 9. And so they arranged it, a guy named Moseley arranged it by order of atomic number. And it put those two elements in the right family. The groups are called families. And cobalt responds with other elements like rhodium and iridium. And nickel over here responds to other elements like palladium and platinum. And so they belong in these individual families. So when they arranged them by the order of the atomic number, the number of protons in the nucleus, they got it right. But each one of these families represents a group of elements that respond approximately the same to other elements. And when you watch that little piece of video, the other video that I have tabbed onto your assignment page. I put the link in there. It's only like 2 minutes. You're going to see that these react with water, all of them. And each one of these families has characteristics that are similar to each other in the family. All right, and so we order the periodic table not by the physical properties, but by the chemical properties of the elements. And they change periodically as you go across. So you got the group 1, the way they respond to other elements. Then you got group 2, and then you go boom, 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 and then you come all the way back, and then you got this group 1 thing that's going on again. So I want you to watch that other little 2-minute video, and I think you'll enjoy it. It will show you how similar chemical characteristics can be grouped up. And by the way they respond to water gets more intensive as you go down because the atom gets bigger. And it's all about the electrons. And if it's a bigger, bigger, bigger atom, the electron is further away from the nucleus to hold it in place. So it's more reactive. It can release more easily. So the bigger the atom is, the more reactive it gets. Over here in the nonmetals, the smaller the atom is, the more reactive it gets, because these are the losers of electrons, over here the blues, and these are the gainers of electrons, the yellows. We're going to talk more about that later. Okay, watch that other 2-minute video, do the quiz. Have a great day.